Good morning. This is Chem 100, our closure notes part 2, and this is Stoichiometry 102. Excuse me, our two topics for these notes are gases at standard temperature and pressure and percent yield. So I just wanted to start off with a really basic statement that we have 3 states of matter that we work with. There's actually more than that, but we're going to only look at these 3. We have solids, liquids, and gases. And then I just made a little kind of table over here, sort of, where I talk about how the molecules are within a solid or a liquid or a gas. Within a solid, the molecules or the atoms are in set positions and they're really close to each other. In a liquid, the molecules are still close to each other, but they have freedom of motion, so they slide past each other in a liquid. And then in a gas, the molecules are spread out and they're moving really fast and they bounce off of each other. Okay. And so what I want to talk about are gases at standard temperature and pressure. Okay, so gases at standard temperature. Standard temperature is 0 degrees Celsius. This is also known as 273 Kelvin, which we'll get to when we talk more about gases, but Kelvin is another temperature scale. And pressure is 1 atmosphere. And when gases are at standard temperature and pressure, a mole of gas has always the same volume, no matter what gas it is. So gases at standard temperature and pressure, 1 mole of any gas at STP, which is what we use for standard temperature and pressure, has a volume of 22.4 liters. Okay, so of course, we can write an equivalence with this. 1 mole of any gas at STP is 22.4 liters. So we can use this in stoichiometry, or we can rewrite this, sorry. I kind of jumped the gun there. We can say 22.4 liters of gas is 1 mole of gas at STP. So this is an equivalence, of course, we can use in a stoichiometry calculation. So we want to remember that to apply this to stoichiometry, we're going to add it in to the stoichiometry map. Okay, so to do that, we want to remember that at its heart, any stoichiometry problem is a moles to moles calculation. So we're always going to have moles that were given or moles known. And then on the right side, we'll have moles of the unknown, whatever substance it is that we're talking about. And to get between the two of them is using a mole ratio. And remember that that's the unknown substance coefficient over the known substance coefficient. And then we also know from our past notes that we can be also given grams of a substance. And in order to get away from there, we have times 1 mole over the molar mass. And if we're asked to answer in grams, then we would use the molar mass of the substance on top and 1 mole on the bottom. So here's our diagram that we had to start with in Stoichiometry 101. And all I'm going to do here is take this information, the moles of, or the 1 mole at STP of a gas is 22.4 liters. And I'm just going to add that in here in red. So if we are given liters of gas at STP instead of grams, we can still convert to moles, but we can use this equivalence right here. If we're trying to get to moles, we would do 1 mole on top, and STP is 22.4 liters. I didn't need to write STP in there, but 1 mole at STP is 22.4 liters. And if we're asked to answer in liters at STP, then we would use 22.4 liters of gas is 1 mole at STP. Alexa, stop alarm.
6:30 a.m. alarm stopped on Hillary's second echo dot.
Sorry, guys. Okay, so what we're going to do is a couple of example problems to demonstrate this. And we're going to use we'll use the combustion of propane. So C3H8. So these are going to be our examples. C3H8 as a gas plus O2 as a gas makes the same two products all the time, CO2 plus H2O as a gas. 3 here, 4 there, yeah. So I'm going to put a 3 there and a 4 there, and that's 6 and 5. Okay, so I'm going to give an example where we're given liters at STP and asked to answer in something else. And then I'm going to do another example where we're asked to answer in liters of gas at STP. So this will be example number 1. We'll say how many grams of O2 are needed to produce, we'll say 25 liters of water gas at STP. Okay, so we're using this equation, and what we're going to do is we're starting with 25 liters of H2O at STP, and we're asked to answer in grams of oxygen. So we're starting here at liters, and we're going to go hop, hop, hop up here to grams. So let's see, I'm going to answer in purple. So we'll have 25 liters of H2O. And we know this is at STP, and the water is in gaseous form. So we'll do our 22.4 liters is 1 mole of water gas at STP. And then we'll do our mole ratio. That will take us from here to here. So we need a mole ratio next. 4 H2O, and then 5 O2. And then 1 mole of O2 has a molar mass, because we're trying to get up here to grams, of 31.998. And this is grams of O2. So our moles cancel, our liters cancel. Let's see what we come up with here. 25 times 5 times 31.998. Divide by 22.4. Divide by 4. And we get 44.6 grams of O2 are needed. Okay, cool. So that's our first example. And I'm just going to go ahead and do the second one. And I'm going to keep this diagram visible. I'm going to try to keep the diagram visible, so sorry for my primitive ways here. Yes. Okay, so we're going to keep with our same reaction. The C3H8 plus 5O2 makes 3CO2 plus 4H2O. And our example 2, and we're going to start with grams and answer in liters. So we'll say if 15 grams of C3H8 are combusted, how many liters of carbon dioxide are produced at STP? So keeping the big picture here, we're starting with grams, starting here, and we're trying to go to liters of gas at STP, so it's hop, hop, hop. Okay, so we'll start with our 15 grams of C3H8, and our first step, of course, is from grams to moles, so we want to convert to moles. And this is 44.096 grams per mole of C3H8. Then we need a mole ratio, and that's going to be a C3H8 on the bottom, so that's a 1. And on top is going to go CO2, which is 3. So that gets us to here. And then we are asked to answer in liters of gas at STP. So we know that for every 1 mole of CO2, there's 22.4 liters at STP. And so we're going to multiply here. 15 times 3 times 22.4, divide by 44.096. And we get 22.9 liters. So just over 1 mole. Okay, that's it for the first part. And then in part 2, I'll come back with percent yield. Okay, thanks. Bye.